Hello everyone, my name is Michael Horn, and today we'll be completing homework 3 for my Process and Dynamics Controls class. And so in this video, I'm going to be working through part A of that homework, in which I will be deriving the transfer function for a singular gravity drain tank by linearizing the dynamical equation relative to the liquid level to inlet-outlet flows. And then we'll also be finding what the gain and the time constant is for the resulting first-order transfer function. So we have our iPad here, and we will work through this and begin our problem-solving methods. So let's begin by writing out some equations that we've used before in gravity drain tanks. Now with gravity drain tanks, obviously height is going to be dependent on time, because how far liquid has to drop will determine a lot in our equation. So we're going to use a equation that we used before when working with gravity drain tanks, and that is going to be the area. It's a little bit bigger here. It's going to be the area with dH over dt, and that is going to be equal to Q in minus Q out. Now from this equation, we're actually able to get this variable and say that that is equal to 2 times gravity. And then we can rewrite this, we'll rewrite it right below, and this will be equal to Q in minus height 1/2. Now from here, we're going to actually incorporate our Laplace transform. So the first thing that we're going to drop my pencil. The first thing that we're going to do is create a graph for this h value and make it a function. So what you're going to do here is make a little chart. So our little graph, and any x to the 1/2, the graph is going to look like this. Let's fix that a little bit. Okay, now on the line you're going to need to label 2 points h and h bar. Now from here you're going to draw a little line up till you get to the point on our line that is equal to h 1/2. And now from here we're going to need to actually find the slope. So we're going to go like this. And then from here we arrive at the equation h minus h bar. And so now we can finally rewrite our h to the 1/2 equation. So we have h to the 1/2, but you can also rewrite that as h to the negative 1/2 minus the derivative of h to the 1/2 over dh. Let's move this over a little bit. And this will be taken with respect to h bar, and then we will subtract h minus h bar. Now, as I mentioned in the homework, we need to linearize this equation. So to do this, we're going to actually set h bar equal to a value of 4. And now we take that value of 4, and we're going to sub it in there. Now, once you do that, you arrive at an equation, I'll skip all of the algebra, of 2 plus 1/4 times h minus 4. So now we have completed the step in which we need to linearize this equation. So now from this point, we're going to go and grab this equation that we had at the beginning. Now that we've completed our linearization, we're going to drag u down. Now, since stated in the problem statement, it is steady state, so we can assume this to be 0. So we're going to rewrite this to 0 equals q in minus h to the 1/2. And now we're going to look at these things called deviation variables. I'll write these down. Deviation variables. Now, these variables, there are 3. The first one is h prime equals h minus h bar. You also have t prime equals t minus t bar. And the final one, if you can guess it, c prime equals c minus c bar. So now that we have these deviation variables, we are going to sub this into our original equation. So again, we take this, we're going to bring this down, but there's going to be a few differences, as this will be H prime, this will be Q prime, and here, this will not be Q out, we will write this as alpha. And then here we're going to actually sub in the equation that we got all the way up here. So this will be h to the negative 1/2 plus d h to the 1/2 dh h bar with respect to h bar minus h bar. So now the final step in this algebraic equation is to say area times dh prime over dt. Again, this is just finishing out this algebraic equation is equal to qn prime minus alpha times, again, this term is going to shrink down after we simplify it, dh to the 1/2 over dh, all taken at h bar, and then this will be multiplied by h to the 1/2. So now, as we said, we are going to incorporate Laplace transform, and to do this, the first thing that we're going to need to do, first off, I made a mistake here, actually, I wanted to address. This is not 1/2, that is actually prime. So the first thing we're going to do is take this value, and since all variables are known in it, we're going to assign it just a term, and we will call this z. So now, using Laplace transform, we will get the equation a times sh minus h prime of 0 is going to be equal to our uppercase qn minus zh. And the final step, my recording kind of cut out weird, so I already have it written down, but I'll walk you through what I did. So last you saw, we were right here. Now anything times 0 is going to be 0, so right here we can cancel this out, and we're left with ash equals qn minus zh. And then finally, once you isolate qn on its side and take out the h, you are left with this equation. Now we have one more Laplace transform to take, and we want to isolate this h value. So we're going to draw an arrow up to here, and we're going to say, this is after the Laplace has been taken, you do 1 h equals 1 over as plus our z value qn. And then we were actually able to square that value and say that this is actually equal to our transfer. So now we will look at this in an actual system. So imagine here we have a gravity drain tank. So now we have this arrow pointing in. This arrow will have our little qn and our big qn. And then coming out the bottom, we will have h and uppercase h. And now to get our equation from this value, we will have our large h is equal to this part where we have right here 1 over as plus z. And then we also need our q value, which is 1 over s. And so when you take these and you algebraically work through them, you arrive at an equation h equals k over tau s plus 1. And now from here we can say, okay, we've seen these before in class. This value is going to be equal to our time constant, and this value k is going to be equal to our overall gain. So now, as a recap of what we've done, we took our gravity drain tank system. We first linearized it and arrived at this equation here. We then took that, used our deviation variables, and arrived at this equation here, which allowed us to find our transfer function. And from here we drew our system, isolated what h is equal to, brought this down, added in our q variable, and we realized, okay, our K is equal to our gain, and tau S plus 1 is equal to our time constant. So now I've completed part 1 of the homework. I hope everyone was able to understand and follow along, and thank you for watching.